Welcome to section 3.4. We're solving equations today with logs and exponentials. I want to walk us through the intro first, at least a couple of them until you kind of get the idea. But I want to do this just so you kind of see why we're going to do some of the steps we do later. If you look at the first one, we give you x plus 2 is 12. If we asked you to solve this, you would say we'd subtract 2 on each side. Why? Because subtraction is the inverse of addition. Okay? We do subtraction because subtraction is the inverse of addition. I'm going to skip the second one. I'm going to go to the third one. If I give you x squared equals 12, in order to solve this, you would square root. Why? Here we go. Square rooting is the inverse of squaring. Okay? We're looking at these inverse words. So I'm going to jump, basically these two are the same thing as these two, but taking a look, 3 to the x is 12. Well, this is an exponential, and so what we're going to do is we're going to log both sides, because a log is the inverse of an exponential. I'm going to kind of shorthand this a little bit. Okay, so the log is the inverse of an exponential. For the next one, because this is a base of 5, what I'm going to do is basically take each side and make 5 the base. And what we do, we call this exponentiation. Exponentiation. Let me make sure I spell that correctly. We're going to make, basically it's going to look like this. I'm going to take 5 to this side and 5 to this side so that my bases would cancel out. Again, the reason exponents are the inverse of logs. Okay, and the same thing then applies to the next one. I'm just going to show you over on the side. I could natural log both sides so that the base e would cancel out. And I'm going to exponentiate each side, e to each side, so that I could again cancel out then e and the natural log. And so that's kind of the goal of today. Again, we're going to do the inverse. If an exponential is left and we don't know what to do with it, we're going to log it. If a log is left and we don't know what to do with it, we're going to exponentiate it. Okay, so let's actually get into some examples. We're going to give you a few hints first. First, rewrite the equation so it allows us to use the one-to-one property. And we talked about this in a couple of the sections. The one-to-one property is going to be huge for us. The second thing, again, we're going to rewrite an exponent as a log, or we're going to log both sides, or write a log equation as an exponential equation, or exponentiate each side. And there are a couple of ways to do this. And so I'm going to show you a couple of different ways to go through, and then you can kind of decide. Okay, the first way would be to rewrite it. So I'm going to look at A. 3 to this power equals 10. If I rewrite an exponential into a log, I say log base 3, because 3 is the base of this exponential, of 10 equals, I apologize, equals the exponent 2x minus 5. This I can use a change of base, so you have the log of 10 divided by the log of 3, and you end up getting approximately 2.096 equals 2x minus 5, and then I think you can solve from there. Add 5, 7.096 equals 2x. Divide it by 2x is approximately, and I'm going to say approximately because we again did round that decimal above, 3.548. Okay, so that's the first method for solving it. The second method, what we can do is, because this is a base of 3, I can just log both sides with a base of 3, so that I get this expression equals the log base 3 of 10. So because this is a base of 3, I can log base 3 both sides, because this base of a log will cancel, and then I have 2x minus 5 equals the log base 3 of 10, and guess what? Then I'm back to where I was before. You could go through and solve. So because you already have a base that's a number, you could just log of that base to both sides. The third option, even though it's not a base e, a natural log does what a log would do. You could natural log both sides. And then here's what happens. I could use my exponent rules to bring this down in front. So I could have 2x minus 5 times the natural log of 3 equals the natural log of 10. And I could divide by the natural log of 3. And this here is, again, the change of base formula just in terms of a natural log instead of a log. And so you're left with then 2x minus 5 equals, and that decimal again was 2.096, and you could solve from there. So you kind of have a couple of options, and really the best way, pick your method and decide. This one, we did some rewriting. Okay, the second one, we did the log base, which was the same as the base of the exponent. And this one, we did the natural log and used our properties. It's completely up to you. They get the same answer. We just want to show you all three methods. So let's flip the page. Let's look at some one-to-one properties. The one-to-one property, if we remember back from the first section, first couple of sections, said basically, can you make these two bases the same? And you always want to use the smaller number, so I'm going to leave this as 3 to the x plus 9. The question is, can I make this 3 to some power? And the answer is yes. It's 3 to the 5th will get you to 43. Okay, so because the bases are now the same, I can cancel those out. X plus 9 equals 5. Subtract 9, x equals -4. Okay, we did say above 2 you'll want to make sure you kind of check things. You really want to make sure you check with logs, less with exponentials. We need to use our properties, and according to our properties, subtraction means divide. So I'm going to take this as the natural log of 2x minus 1 all over 7 equals 0. Okay, now you have a couple of options. You're here with a log, and so you can rewrite this into exponential form, or you can exponentiate. And I'm going to show you the exponentiate. This is a base of e. What that means, in order to cancel it out, is I'm going to take e to this side and e to this side. What happens then is these will cancel out, so I'm left with 2x minus 1 all over 7, and anything to the 0 power is always 1. So then you can go through and solve. I multiply by the denominator of 7. 2x minus 1 is 7. When I add 1, 2x equals 8. And I divide it by 2, and I'm running out of room, but x equals 4. The biggest thing, though, with a log you want to check is, remember, you cannot take the log of a negative number. So when I plug the 4 back in, 2 times 4 is 8, minus 1 is 7, minus the natural log of 7 does get me 0, so this is okay. But if any time you get a number where you plug it in and the log ends up becoming negative, you have to get rid of that, and we call that an extraneous solution. Okay? We're going to look at one more where we use our properties. Again, you'll see that these two are on the same side. I need to condense them. Because there's a subtraction sign, that means we're going to divide. So I've got 3x minus 10 all over 5. I'm going to stick that in parentheses, equals the log base 7 of 2x. And this is a one-to-one property with a log. You'll notice that a log base 7 equals a log base 7, which means they can cancel each other out. So I have 3x minus 10 all over 5 equals 2x. I'm going to get rid of my denominator here a second by multiplying by 5. 3x minus 10 is 10x. When I subtract my 3x, negative 10 equals 7x, and I divide by 7, x is negative 10/7. Now again, you will want to plug this in and just make sure you don't get a negative log. If I plug in negative 10/7 into here, this is fine. You get negative 30/7 minus 70/7. That's a negative. This one would also be a negative. If I look and plug this in, I get a negative. That means this is not a solution, and so we say no solution. This is extraneous because this negative, even just put in here, would make this evaluating the log of a negative number, and you can't. So we say no solution. Okay, and really we tell you to check them. Exponentials are normally fine. It's the logs that you really have to check. Okay, we call those the easier ones. We're going to keep going, a little bit more difficult. We're going to round our answers to 3 decimal places if we get a decimal. So what I'm going to do, I always want to get rid of the number in front, so I'm going to divide by 8 first. 3 to the x equals 11. You again have a couple of choices, like on the front, you can log both sides, you can rewrite it, you could natural log both sides. What I'm going to do is actually log base 3, and I like doing that truthfully because I know then things automatically cancel out. So x is log base 3 of 11, which let's change base this, log 11 over log 3. Therefore, x is approximately, and we said as a decimal, let's go 3 decimal places, 2.183. Okay, and again, you have multiple options. I just like to log the same base because things go away. Okay, let me take 5. We're going to add 12 to both sides first. 6e to the x equals 54. When I divide by 6, I get that e to the x is 9. And because it's a base e, this is an easy one. I'm going to natural log both sides. So x is the same thing as the natural log of 9. If either of these were a no calculator question, if this was no calculator, I'd leave it here. If this were no calculator, I'd leave it here. But if you're allowed to use your calculator and they tell you 3 decimal places, then I'm going to say 2.197. Okay, so I'm just trying to show you, because again, some of these are no calculator, that obviously if you take a look, like 1, 2, and 3 above are all no calculator. 4 and 5 could be as well, depending on how you leave it. Last one in this group, let's get rid of the 7 first. I know some people want to put it up as an exponent. You end up then having to deal with 7th roots and things like that. It gets kind of messy. So let's just get rid of it. Log base 5 of 3x equals 4. You'll notice now I'm stuck with a log. The only way to get out of a log is either to rewrite as an exponential, or I'm going to exponentiate, which means I'm going to take 5 to each side so that my log will cancel out. 5 to the 4th is 625. And if I divide it by 3, okay, you end up probably needing your calculator, or you could leave it right here. You could say, I would say 208 1/3 or 625 over 3 would be kind of the 2 better answers. Please don't say 0.3 repeating and pre-calculate, try to get rid of the repeating ones. Okay, so that starts a little bit, we call them the medium ones. Again, so far, even if I said no calculator, you could leave it here. So far, none of these potentially have really needed calculators unless we're simplifying to a decimal. Okay, so let's go a little bit more difficult. Let me slide this out of the way a second. Okay, here we go. I'm actually going to start with 8 because I think 8's a little easier. We'll go to 7 last. You'll notice 2 logs on the same side, which means we're going to condense them. Addition means multiply. So you have the log of 5x times x minus 1 equals 2. All right, now, there is no base listed, which means it's a base 10. So I'm going to exponentiate 10 on this side, 10 to this side, so that the 10 in the log cancels out. And I'm also at the same time going to distribute. 5x squared minus 5x equals 100. Now, whenever you have an x squared and an x, you have to set it equal to 0 in order to be able to solve. So I'm going to subtract 100. 5x squared minus 5x minus 100 equals 0. Easiest way in this case is to factor. So what I'm going to do is pull out a 5. X squared minus x minus 20 equals 0. And then I'm going to factor. X squared is x and x. Negative 20 is going to be 5 and 4. And the 5 has to be negative in order for it to equal a negative 1 when you add. So 5 times x minus 5 times x plus 4, which tells me that x is 5 and that x is negative 4. And again, we're dealing with logs, so we want to go back and say, is there anything that's a problem? Well, plugging a 5 in, 5 times 5 is 25 is fine. And plugging this in, 5 minus 1 is 4. At least I get both positives, so this one's going to be okay. The negative 4, 5 times negative 4 is a negative 20. And I can't evaluate a negative log. So this is an extraneous solution. Therefore, our only solution is x equals 5. Okay, so yes, you will have some factoring if you wanted, though you could have used the quadratic formula, although I think that's way worse and more time consuming, but factoring is the best method. So let me go back to 7. 7 actually is a factoring question as well, and I'm going to write it a little differently so you can see that, hopefully. E to the 2x is the same thing as saying e to the x squared. So I have something squared minus 3 times that something plus 2. And so if I look at factoring, e to the x squared is e to the x times e to the x. 2 is going to be 1 times 2, but they both have to be negative so that you add to the negative 3. So e to the x minus 1, e to the x minus 2 equals 0, and I'm going to solve both of these. E to the x minus 1 is 0, so if I add 1, e to what power has to get me 1? You only have one possible answer, that's when x is 0. If you wanted, though, and you needed, could you natural log both sides? Absolutely. You just cannot leave your answer as the natural log of 1 because there is an actual nice answer of 0. The second one, e to the x minus 2 is 0. So when I add 2, e to the x is 2. And in this case, I am going to natural log both sides. X equals, if it were no calculator, you could leave it as the natural log of 2. But we're going to round it to a couple of decimal places, so we're going to say it's 0.693. Okay, so it ends up being factoring, and if you can kind of see the starting point of how to say this is squared and then a basic and then a number, I think the factoring then isn't actually that bad. But again, if you have questions on it or not sure, let me know. This is a definite, though, quiz question. We're going to have you factor in e to the x in one of the quiz or the tests. So kind of be aware of that. The last question I have for you is an online banking question. They have continuously compounded interest for 6% each year. How long will it take somebody to, oh, here's the big one, double? Okay, this is going to be on a quiz or a test too, so just kind of be aware of this. If it's compounded continuously, then you're looking at PERT. Well, I'm going to make this so easy. I'm going to make my initial amount 1, so therefore if I double, it's going to be 2. Okay, and that's the easiest way to do it. And so basically, I'm looking at this. 2 then equals, you can put the 1 in, but we don't necessarily need it. My rate is 0.06, and the question is, what's the time? Well, this is a base of e. To get rid of a base of e, I'm going to natural log both sides so that my e cancels out. The natural log of 2, I'm actually going to leave for a minute, equals 0.06t. And if I divide by 0.06, my time is approximately 11.56 years. You could say 11.6 years, something like that. I'm not too picky on the rounding there, and we'll kind of tell you where to round. But again, I'm trying to show you that the easiest way is to set your initial amount at 1, which means when you double it, it's 2. You could use 100 and 200. It just means you'd have to divide by 100, and you end up getting 2. So easiest way is set it equal to 2 and make your initial amount 1. Thanks for watching section 3-4. If you have questions, concerns, anything like that, let me know.